Hi, and welcome to another video. In this video, we do something exciting. Not that the rest of them have been unexciting, they've been super exciting, but in this video, we start to look specifically at some very neat applications of differential equations. Now, we've talked a ton about how to solve them now, and we've done some examples of some applications on what they're used for, but we're going to talk about some very specific things in these next few videos. We're going to talk about population growth, and we're going to talk about how differential equations do a fairly good job at modeling population growth and decline. We're also going to look at some different techniques to look at this. We're going to look at what are called equilibrium solutions and stability, and we're going to look at critical points and how all those play together. But it starts with an understanding of how populations really work and how they can be modeled by differential equations. So in this introductory section, I'm going to show you that. I'm going to show you two very common ways that populations can grow and decline. We'll talk about extinction. We'll talk about population explosion. We'll talk about limiting carrying capacity and limiting population. So those are the things that I want to discuss in this video, and then we're going to unpack that over the next several videos. We'll start with some very simple examples and deal with some ones later that are quite advanced. So let's run through exactly what it is that we're going to be talking about and how differential equations can model these populations. So we all know that populations change, and barring an influx of immigration or people leaving, like an exodus or something, populations generally change depending on birth rates and death rates. So we all know that kids are born and people die, and our population changes, or any sort of population where things are born and die changes over time. And so because our population changes due to births and deaths, it makes sense that how our population is changing can be expressed by births minus deaths. Now note something. Because population is a change in population and not population itself, we're dealing with a rate of change with respect to time, or a time rate of change. And it sounds kind of funny, but it says how the population is changing in a certain amount of time. And that's what we're going to deal with an increment for just a little bit. So think through this. Does a population change? Is that based on births and deaths? Well, it seems so. So how a population is changing is, let's say, births minus deaths. Great. All right. Well, we typically have a birth rate and a death rate in any population. But here's what we mean when we say a birth rate or a death rate. What we mean is a birth rate would be the rate of births per unit of population per unit of time. That sounds kind of funny unless we understand what that is. So let me explain this to you. So when we say, like, it's a birth rate is this, we say a birth rate is, let's suppose, 5 births per 1,000 people per year. Does that make sense? So it's kind of based, it's not kind of, it's based on the population and a time period. And so this birth rate is a birth rate per unit of population per unit of time. It depends on both things. And so we're going to say, all right, well, if the birth rate depends on population, population change also depends on time. So it's related to both of them. In other words, we say, hey, this birth rate is related to both population and the population is related to time. It's going to include both of these ideas. Same thing with the death rate. So our death rate is, all right, how many deaths per 1,000 people per year, or per 100 people per month, whatever it is. It's per unit of population we're talking about, per unit of time. I hope does make sense to you. Let's do a little bit of a recap here. We're going to be talking about how population changes. It's going to be a derivative in just a minute with respect to time. How a population changes is related to the births we have and the deaths we have and the difference between them. So if births are outpacing deaths, if the birth rate is outpacing death rate, our population is going to climb. If the other way is true, if the birth rate is below death rate, our population is going to fall. We'll talk about that. So let's look more specifically at this. So if our birth rate is this beta and our death rate is this delta, and these are all, remember what this is. This is the rate of births per unit of population per unit of time. Well, then let's think about that. So our births themselves, not the birth rate, but the births themselves, the number of births that we have, since the births would be based on the rate of our births per unit of population per unit of time, and the population is whatever it happens to be, some amount, and time is whatever increment of time we're considering, then the number of births would be the rate at which our things, our group of subjects is growing. So the birth rate times whatever population we have at that time times however much change in time we're considering. Now let's go through this real quick. So because a birth rate is the birth rate is per unit of population per unit of time. Let's make sure these units match up. So birth rate is per unit of population. So if I say, hey, this is 5 births per 1,000, and I have thousands here, some amount of population units per year. Well, I have a change in years here, or days, or seconds, or whatever we're considering. So these units would match up to the number of births. I need you to get that. So if this is per population, and then per unit of time, we're going to get the number of births here. Birth rate times population times time. The same thing would happen with our deaths. So the deaths would be the rate at which things are dying per unit of population per unit of time, some sort of increment. Now these are incremental, so this is considering every small little increment. Well, if we put this together, if the way that our population is changing is related to our births minus deaths, and births can be represented by, hey, a birth rate per unit of population per unit of time, and death's the same thing, then let's take this and say, hey, the way that the amount of change of our population, the way our population is changing, can be represented by births minus deaths. Only we're going to use this, births minus deaths. Let's do that right up here. So then our incremental change in population would be about equal to our births minus our deaths. Now let's clean this up a little bit. We know that our birth rate can change with respect to time. We said this is birth rate per population per time, and it can change over time. And so can our death rate, and so can our population. These are all changeable with respect to time. They're all rates of change with respect to time. So I'm going to drop the t here, 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 and here. We're going to keep that delta t, that incremental change in time, for just a little while, just to clean this up a little bit. So our change in population is, remember, birth rate times population times time minus our deaths, death rate times population times time. And we're going to factor out that delta t, and we're going to divide. So if we factor this out, that's a funny looking beta. So factoring out that delta t, we got birth rate times population minus death rate times population, and then we got this delta t. Let's divide that. So we're going to divide the delta t, and we have this birth minus death times population if I continue to factor that p. So all we've done here is said, all right, you know what, change in population should be the way that our births and deaths are related. So let's subtract them and say the change in population would be births minus deaths. We can get positive population growth or negative population growth. That's a decline. We say, all right, that birth rate, what that means is the rate at which we're being born per unit of population per unit of time. No problem. So our total births would be given here. Birth rate times population times time. Death rate times population times time would give us our deaths at a moment of time. That's what that means. So if our population is changing, comparing our births to deaths, then we can subtract our births and our deaths. No problem. That's all we've done. We have factored out our delta t. We've divided by our delta t, and we have an estimate for how our population is changing with respect to time, an incremental change. If we take the limit, then that error should go to 0, and we have this this relationship that the rate at which our population is changing with respect to time is birth rate minus death rate times the population. Now, this is very interesting because this is how a lot of populations actually change, is in some way they are related to they're proportional to the population. This is really strange. We're going to consider two really important cases here in just a bit. So what I want to talk about right now is if our births and our deaths are commonly proportional to our population, we're going to look at two cases on how that is. So one last little recap all the way through, then we're going to talk about these two cases and see some really, really cool things about it. I'm going to go super in depth onto why it is that sometimes we get what's called a carrying capacity or a limiting capacity. We have a threshold. We have a bounded situation with our population, and sometimes we don't. Sometimes we have extinction, or sometimes we have explosion. So in one of those two cases. So we're going to talk about that for a really long time. This will be a long video as far as my explanation is concerned. Now, our birth rate and our death rate can change. They're typically always changing. And there's two really important cases that we're going to consider. One, and there's more than this, there's more than just two, but these are two very important cases. One is, oftentimes, as our population increases, the rate of births decreases. Now that can be due to intelligence of the species saying, hey, there's not a lot of resources here, so if we make more things, they're not going to be able to eat. Or just sometimes naturally this just happens, where the rate of births is decreasing as the population is increasing on a linear type of scale. And we're going to look at that. The other case is, what if we don't have something that's thinking about that or considering that or is not following that model? Sometimes birth rate is just straight up proportional to population. So as the population increases, the birth rate also increases. As the population decreases, the birth rate also decreases. That could be due to just availability. So let's say that there are lots of males and lots of females, and they're getting together and they're doing what bunnies do. That population could explode. But wait a minute, what if the population is declining? Well, then there's less males and there's less females and they're not meeting as often. That population can become extinct. We're going to look at that right now. So two important cases are, what if the birth rate is decreasing as the population is increasing on a linear scale? I want to also mention that in both these cases, we're going to consider the death rate to be constant. So now that doesn't mean that for 1 billion bunnies, we only get 5 deaths. So what that means is that the rate of deaths per unit of population per unit of time is staying the same. So old age, things are dying of old age or something, or some other factor that's in there. But we're not going to consider that to be changing for these two examples. Can it change? Of course, and I will show you some examples of that. There's lots to this, which is going to take several videos. So two important cases we're going to consider where the death rate is constant is, what if the birth rate is decreasing as our population is increasing on a linear scale? So how would that look? Well, then our birth rate would be some initial birth rate minus some birth rate that's related to our population. So can you see how this would, firstly, can you see it's linear based on the variable p? Yeah. Can you see that we would start somewhere? Can you see that we would have a negative slope? So our birth rate would be declining as our population increases. The population is a positive number. So if b sub 0 is positive, so we start with some sort of birth rate that's positive, and we have some sort of population that's growing, whatever this number is, this positive number is, well, our birth rate is going to be declining. Notice we'll still have births, but the rate at which they're born per unit of population for every time period is going to be declining as our population gets bigger and bigger. And as our population gets smaller and smaller, it would increase. So they're inversely related. That's the idea. Okay, well, and our death rate would just be, let's see, what would our death rate be? Well, if our rate of death is not changing, if it's constant, then let's just call this the initial death rate. Delta sub 0. Why would that be a constant? Well, if it's not changing, we can just say whatever it is at the beginning, it's going to be there forever per unit of population per unit of time. Now what we're going to do is say, all right, provided that change in population is births minus deaths, we figured out a birth rate and a death rate, so we figured out births and deaths in relation, well, in terms of that birth rate and death rate. And we factor some things, we did a limit, we have this relationship, the change in population with respect to time is birth rate minus death rate times population. Guys, that's got to make sense. It's got to make sense that the way a population is changing with respect to time would be the difference between the birth rates and the death rates times the population. It's almost I know I went a long time through this, but it's almost an obvious statement. So yeah, the birth rate minus death rate gives you kind of a rate of change per unit of population. So multiplied by the population, you'd have the rate at which this is changing with respect to time. All right, so if our birth rate is dropping as our population is increasing linearly, and our death rate's the same, we're going to take this, we're going to substitute this for our births, this for our deaths. So our change in population, our time rate of change, population with respect to time, would be this initial beta, initial birth rate, minus some birth rate that's changing with our population, minus our death rate that's always constant, times this population. This part is this. We just said we have an initial birth rate and we're dropping as our population increases linearly. And then our death rate is held constant. Man, here's what we're going to do. We're going to distribute all this stuff and we're going to group some things together. So let's look at the change in population with respect to time. Now let's say, all right, so let's distribute the P. And then what I want to do is I want to group this together so that I have my, all right, so that I have my p's out front and my p squared at the back. So I'm going to do this. Just so we can see what factors and what doesn't. And I'm going to factor out the P from here. I'm going to put my initial birth rate and my initial death rate together. And then what we're going to do is we're going to factor out a P. So when, we're going to factor out a this birth rate that's changing with respect, that is affecting our birth rate changing with respect to the population. We're going to factor out this beta sub 1 and P from both of these. And what's going to happen, we're going to force this guy to factor. So we're going to be dividing that. So I'm looking at this saying I can certainly factor out a P. We'll put that up front. I'm also going to factor out this right there. That that birth rate that's affecting our total change in birth rate. It's going to be held constant. So let's factor that out. So if we do that, we have this beta sub 1 population, and then inside we're going to force that to factor. So factoring means divide. We're dividing by the beta sub 1. That would be beta sub 0 times delta sub 0 over beta sub 1. We factored out the P minus P. Let's make sure that this works, man. It's a lot of stuff. So if we were to distribute this, beta sub 1 would cancel. We'd get beta sub 0, delta sub 0, and a P. That's this. And then if we distribute here, we'd get this beta sub 1 P squared. That's this. These are the same exact expression. Now, a lot of times in your textbook or whatever you're working out of, you're not going to see that. You're going to see this. You're going to see, suppose that this and this and this and this, same thing, are all held constants. If they're held constant, then let's call this one K. Let's call this one M. And you get something that you might have seen before, or you might you might see it now. Like, where did they get that? They got this expression, and there's a lot of things hidden in there, isn't there? They've got this expression by saying this constant right here, and it is a constant. If I hold our initial birth rate, initial death rate, and the way that that's changed, well, the thing that affects our total birth rate change, if I hold those all to be constant, then this right here is a constant, we call it m. This right here is a constant, we call it k. This right here is called the logistic equation. So if we hold these things to be constant and all positive, then what this is called the logistic equation. You might want to note that for a second, because this happens in a lot of population change, is that we have something that our population, the rate of births is decreasing as our population is increasing, but death rate's held constant. It's going to yield something called the logistic equation. Now, I'm going to make a statement right now before we go on to the next thing. So I'm going to have to go through this one last time. I'm going to have to erase some of this and put the logistic equation right here. And then I'm going to talk about what if birth rate is proportional to population. We'll talk about what happens here. Then I'm going to go, and if you don't want to watch it, that's fine. I'm going to go behind the scenes. So I'm going to talk about everything you really need, and then I'll talk about the reasoning behind that in kind of a quasi-proof sort of thing to verify what I'm saying. So if you don't want to watch the rest of that, you just want the bare bones basics, here it is, for the first part at least. When we did all this stuff, we said the rate of population change is related to births minus deaths. We got all this stuff down. Then we said, okay, if our birth rate is decreasing as population increases, but death rate is held constant, it's going to yield, here's all the math behind it, something called the logistic equation. This is the logistic equation if this and this are all positive. What's it mean if they're all positive? That means that we start with a positive birth rate and we're subtracting something that is based on population. Population is always positive, and if this is positive, then this means that our birth rate is decreasing as our population is increasing. We have to have this positive, otherwise, if that was negative, obviously this would be growing as population increases. That's our next case. And so this would say that if these are all positive, our death rate staying the same, and is positive death rate. That should make sense. We have a positive initial birth rate that is actually positive, and a way that our population is making that decrease linearly. That's going to yield that logistic equation. We just end up calling this whole thing, which is constant, a different constant, and this our constant k. So I'm going to talk about what happens in just a minute. I'm going to erase this little bit. I'm going to rewrite that logistic equation. All right, so let's take a little closer look at the logistic equation. So let's take a closer look at what would happen if our birth rate is decreasing as our population is increasing on a linear scale. We get this logistic equation. What's going on? Let's suppose that our population, our initial population, starts with m. If p equals m, you are not going to get any change in your population. You're going to get this equilibrium solution, this thing that says you're not changing at all. You have managed to keep your population at exactly this level forever. Your birth rates and your death rates would even out, and since your population's not changing in this case, then your birth rate can't change, your death rate's held constant. It's going to be the same exact population all of the time. We call that, when we get there, a carrying capacity or a limiting capacity. So we're going to explore that in just a second. But if your P equals your M, there's no change. Now, what would happen if P is greater than M? What would happen if P is greater than M? Well, if P is more than M, you get this negative. Do you see that? If that's negative, this is positive. That's population. This is positive. We held that to be a positive constant. Then that would be a negative. If P is greater than M, that's a negative. That means the rate at which your population is changing with respect to time is negative. That would be a declining population. You go, okay, so wait a minute. If our population, so M is a really important number. If our population is greater than that M, then this is going to be a negative and our population will decline. That's going to be a population decline. What if our P is greater than, less than M? If our P is less than M, our population is less than M, our initial population, then what's going to happen? Well, if our initial population is less than M, then hey, that's positive. Remember, that's positive. This is population, it's always positive. If P is less than M, this is positive, and we will get a population increase. It says the rate at which our populations change with respect to time is positive. Do you remember about slopes, about these first derivatives? And if it's positive, our slope is positive, and our function is increasing, this would give you a population increase. Now, I'm going to verify this next statement for you in the next part of this video, but yes, this would be a population decline. So imagine this. We have this number M that's based on a comparison of birth rates and death rates. If it is greater than P, you get a positive here, so P is less than M, and that would be a population increase. And if the opposite is true, if M is less than P or P is greater than M, we get a population decline, but only until we reach M. Why? I'm going to show you that in a little while. But this would be only until we reach M. So here's the idea. We're going to have this M. That's a constant. Constants are horizontal straight lines. So we're going to have this M like this. If our initial population is below that M, right, we are going to get a population increase until we hit M. If our P is greater than, our initial population is greater than M, we're going to get a population decrease, but only until we get to M. M, this number M, is called our limiting capacity if we reach it from the bottom. So if our population starts below it, we get up to it, it's called our limiting population. And if it's something that we fall down to, it's called our carrying capacity. So M is this value that's either a carrying capacity or limiting population. Explain that one more time. It should, just from looking at the rate of change of population with respect to time, if that is positive, then it's growing. But how far? It's going to grow until you reach M, because at the moment that you reach M, you stop. So right there you say, okay, M is called our limiting population in that case. So if M is above P, we go, oh, we're getting up to it. So we're growing. But the closer we get, look at that, the closer we get to M, so if P is below it, P's positive for sure. But we're growing. So if the population initial population is less than this value M, then our population is growing. That's a positive value. But the closer we get, so the population is growing, but the M is staying the same. The closer we get, the less and less our population is increasing, to the point that right here, when this P equals M, we no longer change anymore. We reach it and we stay there. Or we get really, really, really close. Well, what if the other's true? What if we start up here? If we start with our initial population as greater than this value M, well, then what would happen? Well, that's negative. If this piece of 0 is greater than M, then that would be negative. And we would say that our population is declining. That makes sense. But the closer we get to it, the closer that our population gets to this constant M, the less and less and less we're declining, to the point where we're asymptotic to that. We reach what's called a carrying capacity. So depending on where we start, we call this M, this thing that we're going to end up at, either a limiting population or a carrying capacity. I hope that makes sense to you. I hope that I've explained it well enough that you understand this thing called the logistic equation. That at some point, no matter whether we're above or below this value M, this constant value M based on birth rates and death rates, that we're going to reach it. This right here is called a funnel, and we're going to talk about funnels and spouts in the next few sections coming up. We also talk about stability and things like that, but what this is saying is that if you start here or here, you're going to eventually reach this solution, this carrying capacity limiting population. Now, what if this is not the case? What if our birth rates are not declining as our population is increasing? Well, if that's not true, if our birth rates are not declining as the population increases, but are proportional to it, then our beta would be directly proportional to our population. We're going to go right back to here. We said, all right, if that's the case, then the way that our populations change with respect to time would be, well, beta would be this proportional to a population. We'd still get this delta, and we have still a population. I want you to make sure that you're with me on here. This represents every sort of situation, right? So we're going to always come back to this and say the way our population is changing with respect to time is some comparison of birth rate minus death rate proportional to the population. Okay, so let's suppose that our birth rate is also directly proportional to our population. It's not declining. It's not declining as our population increases. It's proportional to it. All right, well, that means that as our population goes up, the birth rate could also go up. Well, that's crazy. Does it make sense? Does it make sense? Like if there's more things in an area, they could breed much, much more. Without a limiting factor, this thing's going to explode. Or if there's less things in the area, they might be breeding less. This population might become extinct. It's a different situation here. So we're saying, let's suppose the birth rate is proportional. Let's make this K times P. Let's hold that death rate to be constant. Okay, we're going to do something just a little bit tricky. So what we're going to do is I'm going to move this P to the front. Now what I'm going to do is I'm going to force this thing to factor out a K. If I force this to factor a K, then we're fine here. We just get P. But I have to divide. Factoring means divide. So I'm dividing out a K. We're going to get this constant death rate divided by K, which was, actually remember that was that B sub 1, beta sub 1 that we had. Now, if I define this to be an M, so let's just call this M, another constant. Then here's what's going to happen. In this case, M is no longer called our carrying capacity or limiting capacity. M is called your threshold. And here's what happens. It's wild, but check this out. If your initial population is greater than your M, you have a positive changing population. Remember, this is slope, man. This is how our function is changing. So if our population is greater than our threshold, then that's a positive slope and it will never slow down. It's just going to increase and increase and increase. Imagine this. So this is greater than M, and if it's still increasing, it's going to be even more greater than M, then more greater than M, then more greater than M. Your population, your slope is just going crazy. Your slope is so positive, your population is exploding. So if M is your threshold, then if your initial population is greater than M, you're going to get a population explosion. I think they call that like a doomsday. So it explodes to so much that there eventually won't be any food. So I'm going to say explosion, so population explosion. What if your population is below that threshold? Well, if your population is below that threshold, then look at this. If your population is less than M, population is less than M, so then this would be negative. The rate at which your population is changing with respect to time is negative. It's declining, but it doesn't ever reach M. It's always below that. If your population starts below M and you subtract from it, well, then it's even more below M. Your slope is even more negative. You're going to get extinction. So what I'm going to do is I'm going to spend some time to go through, I'm going to show you this. I'm going to show you why this is, because a lot of times it's not explained. A good teacher would probably just do what I just did and said, "Yep, you know what? Here's a few things. Number one, the way that population changes is related to births and deaths. It's pretty obvious. Number two, if if we have this rate at which our population is changing is a birth rate minus death rate times population. So, and somehow it's proportional to this in some manner speaking. We have two very important cases. There are a lot more cases, but here's two really common ones. Number one, our birth rate sometimes decreases and our population increases. And we studied all through that. We got the logistic equation and we said, all right, here's the thing about it, is that if our population is less than our M, we're going to eventually reach it. We're going to grow. It's going to be positive growth, but we're going to reach it eventually. And as this gets closer to this slows down, slows down, slows down, slows down, slows down until we finally hit it. If the other way is true, if our population is above it, it decreases, 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 but at a decreasing rate, and then we're going to hit that carrying capacity anyhow. So that's what happens with our logistic equation. But what if the other case is true? What if another case is that our birth rate is just directly proportional to our population? As it grows, birth rate grows. As it declines, birth rate declines. Well, then what would happen here is that we have what's called a threshold. And as your population is above your threshold, the rate of change just keeps on increasing without bound. This is bounded. This one's not. Or if it's below the threshold, it's decreasing and it just keeps on decreasing to an explosion or to an extinction. A lot of times your class is going to stop right here, and that's okay. If you want to know why this is and why this is, I'm going to do some pretty hardcore math. We're going to talk about partial fractions. I will take this and I will take this and we're going to use it as a differential equation. We're going to solve for P, and you're going to see why this is a carrying capacity. You're going to see why this is an extinction or an explosion idea. So hang on for a little bit. I hope that I've explained to you the way that population change is related to births and deaths. I hope I've explained to you these two important cases. There are more, but the two important cases where if our birth rate is decreasing as population increases, we get a bounded situation. I need that to be the case, okay? I also need you to understand that if we don't have that, if we have that the birth rate is always just proportional, we have this unbounded situation. Should be kind of makes sense, right? If we have a birth rate decreases, population increases, you're going to hit a bound at some point. But if you have it growing as just directly proportional, it's going to be unbounded. We're going to explore that in just a minute. Okay, so now that we should have a fairly good idea about how population change is related to birth rates and death rates. And we had two very important cases. We have that logistic equation would mean that the birth rate is increasing as population is decreasing or decreasing as population is increasing. They're inversely related. I hope that I've made it make sense that if that's the case, then remember that your birth rate's your slope. And if we start up here, that your population would look like this. Your birth rate and the rate of change of your population, your slope will be increasing as your population is decreasing. Do you see that? Your population is going down, your birth rate's going up. Or vice versa, if our population is going up, our birth rate is decreasing. The rate at which our population is slowing down. It's decreasing. So increasing at a decreasing rate or decreasing at an increasing rate compared to our population. What that's going to do is always give you some sort of a bounded situation. It has to. This one's not that case. This one says if you have a threshold, if you start up here, you are increasing at an increasing rate. Or you are decreasing at a decreasing rate. Your slope is negative, it just keeps on getting more negative. That's explosion or extinction. I'm going to show you mathematically why that happens, not just show you in a picture. I'm going to show you mathematically. So we're going to take that, we're going to solve it. It's going to take a lot of time. All right, so because that's a differential equation, you go, man, I know all about that. I know that that is separable, and you're right. So let's go ahead and group our P's dP. and our constants dt. And let's take an integral. Now on the left-hand side, we're going to get something that's partial fractions. You go, partial fractions, man, I haven't done that in a long time. Yeah, we're going to get partial fractions. Do you remember this? How we can say this, this fraction can be separated as a over p plus b over m minus p. You go, yeah, okay, I remember that. I remember that 1 equals a times m minus p. We're just getting some common denominators and setting them equal to the numerator. Might have been a long time for you. Plus bp. If I let p equal 0, then if p is 0, let's see, that's 0. This would be a, 1 would equal a times m. And so a would equal 1 over m. And if p equals m, so p equals m, this would be 0, this would be m. 1 equals bm. And b would equal 1 over m. So in both cases, we're going to get this 1 over mp and 1 over m times mp. I'm going to show that right now. So we've used partial fractions. If you don't remember that, I'm going to put a link up there so you can follow partial fractions again. And we're going to get that this equals, let's see, a is 1 over m. So 1 over mp plus b is also 1 over m. 1 over m times m minus p. dp. On the right-hand side, we get this kt plus some sort of a constant. And yeah, we do need it. We don't need it on the left-hand side because we would absorb it, but we do need at least one constant here. We'll see why in just a bit. So, oh my gosh, well, hey, you know what? Those both have a factor of 1 over m. Let's pull that out. Another thing that I'm going to do, and this is going to seem kind of weird at first until you realize why I'm doing it. So what I'm going to do is I'm going to pull out a negative. I'm going to factor out a negative as well. So I'm going to put this 1 over p plus 1 over m minus p dp. What I'm going to choose to do is I'm going to factor out a negative. I'm going to say, all right, let's make this negative. Now what would happen if I factor out a negative is I'm going to get negative 1 over p plus, this is going to give us 1 over p minus m, not m minus p, because I factor the negative and we change that sign. Now, I'm actually ready to do this integral. If I integrate this, this would be a negative 1 over m, and we would get, let's see, 1 over p, that's ln absolute value p, but I have a negative in front. So ln 1 over p gives me ln absolute value p, negative in front. Same thing happens here. You can do a u sub, but because we factored out that negative right there, we factored negative, change our signs, because we did that, remember our variable's p. We don't care about the m. We don't have to use a u sub like at all. There's no negative here. This would just be this plus ln absolute value p minus m. And yeah, we have a constant, but we would get reabsorbed. Hope I'm making sense so far. Now, here's what I'm going to do. I'm going to do two things right now. I'm going to multiply both sides by negative m. That's going to clear this. That's going to give us something being multiplied here. I'm also going to say, do you remember that ln of m minus ln of n will give you ln of m over n? Do you remember that we can combine two logarithms being subtracted by dividing? We have a logarithm minus a logarithm. We're going to make that a quotient here. So I'm multiplying my negative m. I'm also combining this. We're going to get ln absolute value this over this. And I've multiplied by m. I've also distributed. We're getting there. It looks nasty, but we're sort of getting there. Now we're going to make an exponential on both sides. So e to raise to both of these as exponents is going to give us this p minus m over p equals, I'm going to do a couple fancy things here. If I do e here and e here, do you remember that I can separate my exponent? I can take e to both of those terms, and this would give us this e to the negative mkt times e to the negative mc. That right there is a constant. If I wrap up my absolute value in a plus and minus, this whole thing is going to be one giant constant. So all of this is going to change, and this is going to give us a constant e to the negative mkt. I know that that's kind of quick, but we've done this so many times in this course. So we know that this is going to be e to the negative mkt. We know that this is going to be e to the negative mc, plus and minus from the absolute value. We wrap all of that idea into a constant that's being multiplied times e to the negative mkt. Now, we have to solve for p. So here's what we're going to do. What we're going to do is two kind of weird things. Number one, I want to get rid of that constant. You go, how in the world are you getting rid of constant now? I'm going to do it here because every population has an initial value, doesn't it? So when we take a look at an example, the population at time 0 is going to be an initial population. Now, I'm going to plug that in right now. I'm going to get our c, and our c is going to equal p sub 0 minus m over p sub 0. But I'm not going to plug it in until later. Why? Is because it gets real nasty if we try to do that right now. Really, really, really crazy. So what I've done, I've gone all the way through this as far as fractions. I've just integrated. We got this trying to solve for p. I want to also solve for c in terms of our initial population. And so I'm going to plug in 0 for t. I'm going to plug in p sub 0 for p. Remember, this is a function of p based on time, population based on time. That's a constant, that's a constant, that's a constant. That's our independent variable, and then our p is our dependent variable. So we're solving for p, and right now I plug in 0 for t and get p sub 0 for the p in relationship to that 0. I'm going to get my c, but I'm not going to plug it in yet. So if I plug in 0 for t, notice this, look at, if I plug in 0 for t, this whole thing would be 0. This whole thing would be 0, this would be 1. I would get p sub 0 minus m over p sub 0 equals c times 1. C is this right here. So I'm going to write that to the side. I'm going to say c is p sub 0 minus m, worst m ever, over p sub 0. We are going to use that in just a minute, I promise. But before we do it, before we plug it in there, let's leave this where it is because it's much nicer to work with right now, and let's solve for p. We're going to multiply both sides by p. We're going to group our p terms on one side and our m term on the other. So I'm going to subtract this from both sides and add our m. So we've subtracted this. We're going to add our m. Let's factor that p since we have two terms. And let's divide to solve for p. Now, I promised you we're going to come back to this, but do you know, I mean, that was a lot nicer to do with that c, but we do have our c right here. We're going to now plug in that c because we want this in terms of p and m and a constant k with t as our variable. Remember that m is a constant, k is also a constant. We know what those things were. We defined them for the logistic equation. And then that c, we now know what that is. That c is this p sub 0 initial population minus m, a constant, over p sub 0. So I'm going to plug that in now. So our population with respect to time is some constant m based on birth rate and death rate. 1 minus c is that p sub 0 minus m over p sub 0. So that is c times e to the negative mkt. Now, that might not look very good to you, but we are almost done. All we're going to do, because this is a complex fraction, and you know how to clear complex fractions, right? We know how to multiply by p sub 0 over p sub 0. Just multiply by the LCD, your denominator. Yes, this is going to multiply, give you something very nice, m times p sub 0. This is going to distribute. It will cancel this fraction. This will have to go in parentheses, but it will also go to your 1. So we're going to get m times initial population over initial population minus, what I'm going to do here is I'm going to cancel this p sub 0. We're going to get p sub 0 minus m e to the negative mkt. Now we're going to do one other thing that's going to help us to see this a little teeny bit better. What we're going to do is we're going to factor out a negative here. Remember how we factored a negative way back here and it made things easier? We're going to sort of undo that right now. So we're going to factor that negative. In other words, we're just going to reverse these and change that sign. So factoring that, that would be p sub 0 plus m minus p sub 0 e to the negative mkt. I go, how in the world is that going to help me see anything? Okay, great. This is your population. So we just solved a pretty heavy-duty differential equation with a lot of stuff. And you go, okay, we got down to there. That's fantastic. What's going on? What in the world would happen here? What we're going to look at is the relationship between m and your initial population. What I told you was that in the logistic equation, you have this m that is like this flat, but it's obviously constant, so it's this horizontal flat line. And I told you that if your initial population is below it, and we logically went through it, but I'm showing you right now, if your initial population is below it, you will have an increase in your population until you reach it. If you have an initial population that's above it, you're going to have a decrease in your population until you reach that m. It is called a limiting population or a carrying capacity, depending on whether you're increasing to it or decreasing to it. Let's see why that is. It's very important you're able to look at these functions and understand what's going on. This is your population. It is what's going to happen. Now, you know that an exponential, doesn't matter what this is, that exponential, it is positive. Do you see that? Like, that's a positive number. Now, how the size of it, I don't really care right now. It's a positive number. Here's what I want you to look at. What happens if p sub 0 is less than m? If p sub 0 is less than m, if p sub 0 is less than m, then this is a positive. Think this through. M minus something less than it would be positive. That's already a positive. Then this right here would be a positive number. What that means, if p sub 0 is less than m, then this is positive, right? So you take this initial population that's positive, you add something to it. This would be, then your population, then this whole thing would be less than, I can't write it there, I'd have to write it up here. So this would be less than the population times m over the population itself, wouldn't it? So if this thing is positive, then this is a bigger denominator than this. Then this fraction would be less than this fraction, and this would be less than m itself, which means your population would be less than m. So if your population, and this equals m, if your initial population is less than m, sure, you're increasing, but you're bounded. We've just proven that this would be bounded right here. You said, man, if this is positive, we know that's positive, then this is a number that's bigger than p sub 0. What that means is that this fraction is less than m times p sub 0 over p sub 0. That's an upper bound. If we simplify that, that upper bound is just m. It says that yes, if your population is below m, it's going to increase. We saw that in our differential equation, but it's going to increase until you're bounded by m. That's what's going to happen. Now, what would happen in another case? What if your p sub 0 initial population is greater than m? If your initial population is greater than m, if this number's bigger than this number, remember that this is positive. If this number's bigger than this number, this is negative. Negative times a positive is a negative. You take something positive minus another number, this would be smaller than p sub 0. Therefore, this fraction would be bigger than m over m times p sub 0 over p sub 0. This would be bigger than that. Look again. Positive number times negative number. P sub 0 would be greater than m. That would be a negative times a positive and negative. Something, a positive minus a negative. Okay, this is going to be smaller than p sub 0. Therefore, this fraction is bigger than this fraction. But this is m. That gives you a bound. It gives you a lower bound. So what's happening here? Man, I know there's a lot of stuff. I hope I haven't confused you. But what's happening here is we know that two things. That if this was the case, our population was going to be increasing. We saw that from right here. I'll put everything together for you right now. If our initial population is less than m, get this, if our initial population is less than m, this is smaller than this. That's a positive number times a positive number. Positive. That means our population is increasing. Okay, so this case right here says population is increasing, right? It says that. But it also says that our population has an upper bound. It says that you're increasing, but you are only increasing until you get to m. It can't be any other way. Now, what if the other case? What if our initial population is greater than m? This is bigger than that, gives you a negative. It says population is decreasing, but we have another bound. We're decreasing until we reach m. So in either case, for the logistic equation, we're going to reach m, this carrying capacity or limiting population. That's all that can happen. Now I'm going to erase this. I'm going to talk about the next situation, but I'm not going to go through all of this work. It's extremely similar. You're just doing... I'll show you in a minute, but let me erase this stuff and we'll come back and talk about this. All right, so last little bit, we're going to talk about the explosion and extinction. We just learned about the logistic, how we have this limiting population or carrying capacity because of the relationship between an increasing population and a upper bound, or a decreasing population and a lower bound. It's going to happen that way with the logistic equation. Now, what if we have this other case where our birth rate is just directly proportional to the population? So as population grows, birth rate also grows without bound. Or as population decreases, birth rate also decreases without bound. They're directly tied together. You would go through exactly the same idea all the way down, and you solve for p just exactly like I showed. I'm going to show you again, same stuff. But you'd end up with something like this, and I want to talk about why this population is going to explode or become extinct. Let's look at it. What if your initial population is greater than m? Notice, that's not negative, so this is not This right here is still positive, but it's growing pretty fast generally. Um, so let's look just here and focus on this. What if your initial population is greater than m? As we go forward and go forward and go forward with this situation, then if this is positive and this is getting bigger and bigger and bigger, then the difference between your initial population and something that is positive, look at this, the difference between initial population and something that's positive, this is going to get smaller. Remember, this would be positive. Positive and growing. So we have some initial population that's getting, and where the population is shrinking, smaller and smaller, this is getting bigger, this is staying the same, smaller, 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 this is a constant. So wait a minute, you're taking a constant as time goes on, you're going to get number over number that's shrinking. This is going to go to infinity. That's going to go to infinity. As t approaches infinity, remember this is constant, that's going to go to infinity, this is positive, this is going to get really, really, really big, this is going to stay positive, number minus really big number. As we get close to that population, initial population, this is going to get very, 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 very small. Divide a constant by something very, very, very small, you're going to get infinity. It says that if you have a threshold of m, and you start here with an initial population above it, if the initial population is greater than m, it is going to eventually explode. There's no bound. Now, the other case, if our initial population is less than m, that's the same. This would be, man, well, this would be, that would be something really large as t goes to infinity, but this, if p is less than m, this becomes a negative. A negative times a positive is a negative. But wait a minute, you're taking a positive number and you're subtracting it, you're adding to it. So you're getting this denominator that's growing bigger and bigger and bigger and bigger and bigger and bigger and bigger, not getting closer to some initial value, not getting closer to zero, you're getting something that's getting bigger and bigger, closer to infinity. Take a constant and divide by something getting closer to infinity, and you're going to go to 0. That means that if your initial population starts below your m, you are going to get the population is decreasing and continues to decrease. You're going to get extinction. I really, really hope, this has been probably one of the most brutal lessons as far as theory that we've ever had. So I understand that it's really heavy duty. I said a lot of things in this lesson, and if you stuck with me, good job. You're going to be fine. In the next few videos, I'm going to do a lot of examples to illustrate these concepts, to show you from some very basic stuff, some pretty complicated ideas. What we've done in this video is I've shown you that the way that population growth I've shown you how population growth relates to birth rate and death rate. I've shown you two very important cases where birth rate declines as population increases, or birth rate increases as population declines. I've also shown you how another relationship where birth rate is directly proportional to our population. And we've seen that for the first example, the logistic equation, that we are going to reach some sort of threshold. What I want you to understand is that if birth rate is decreasing as population's increasing, if it's inversely related, that you are going to reach some sort of a bound. The opposite, if birth rate is directly related, directly proportional to your population, you're not. You can have a threshold where if you're above it, climb forever. If you're below it, you fall until you reach 0, in this case. I hope that makes sense. I will see you for the next video. We're going to start just two very basic examples on how to set problems up. And then as we go forward, we'll be talking about this and exploring extinction and explosion. And we'll also be exploring the logistic equation in several more videos. So hope you enjoyed it. That was crazy. And we'll see you for another video.